So the next speaker of this session is Dr. Shekhar Tomar. He's in the Indian School of Business at Hyderabad, and he's going to talk on shock diffusion. Does inter-sectoral network structure matter?
First of all, thanks a lot to the organizers for having me here. It's a pleasure. So the first two sessions were very thematic. So now this is like a very micro question which I am going to talk about today. And I'll probably trying to convince you guys that macro is interesting. So although Andreas gave a big diatribe about like how he doesn't like experimental guys, but me as a macroeconomist, I just don't like them for a certainly different reason. But I'm not going to go deep into it because anyway, everyone hates economists for jumping on everyone's toes. But let's get started. So what I'm going to talk about today is a very specific topic which has kind of interested economists for a very, very long time. And the big question that I'm going to ask is, can idiosyncratic sectoral shocks, can they generate aggregate volatility or not? So what do I mean by it? So generally, when economists talk about GDP, we all know that there are some business cycle fluctuations. We usually see that economic activity goes up and down. So normally, when they try to model these fluctuations, they assume some kind of a volatility in the technology parameter. So they say, okay, the technology gets some shock every period, and that increases or decreases the productivity, and that leads to change in the overall GDP. So now the big question is that in a lot of these cases, people just assume that this technological shock, it is driving the aggregate fluctuations. But then we haven't really unpacked what is exactly lying inside those technological shocks at the aggregate level. And so one of the ways you can think about what constitutes these aggregate shocks is a summation of sectoral level shocks. Now, if you think of it from a law of large number argument, so imagine there are a large number of sectors, and each of them receives these idiosyncratic, maybe again, technological shocks. But if you have these large number of sectors, can it again impact the economy at the aggregate level or not? And so if you have this law of large number argument, then as the number of sectors increases, the impact of any single shock should wash out in the aggregate. So effectively speaking, they are canceling out each other rather than leading to some aggregate fluctuations. So this has been a standard argument for last 20, 30 years, which started to get broken down recently by some work thanks to the network structure. So the idea is the following, that, okay, these sectors, they can have idiosyncratic shocks, but they are not alone in the universe. They are actually interconnected with each other. So now if these sectors are interconnected with each other, then these idiosyncratic shocks can actually get amplified when you look at the aggregate level. And so the amplification of these shocks, it depends on the network structure. And usually there are other frictions which can aid this kind of amplification. If, let's say, consumers don't react at the same time, or they react with a lag. So those kind of things can actually aid this amplification. So just to give you an idea in what kind of a network setting that you would expect sectoral shocks to generate aggregate fluctuations. So here we have a very fully connected network. So each of these individual nodes, they're interconnected with each other. So you can think of it that they're buying stuff from each other. And so now, if any single one of them gets hit by a shock, it's going to transmit it to others, but only so much. All of them are getting impacted, but compared to this network on the right, which is a star network, these 4 downstream guys are buying from this just single one guy. So if you hit this upstream guy, by a technological shock, it's going to impact all these downstream guys. So essentially what you need is some kind of a star network, that there are some star sectors, or you can think of it even from a firm level perspective. If there is this one big firm, let's say Amazon, it goes bust, then a lot of the retail trade would be affected. So, and we find these kind of star networks everywhere in the economy. So how do you actually break down a law of large number argument? So some of you are physicists and mathematicians here. If you have some kind of a Pareto or like a 80-20 rule that there are some stars in the network, that is what you need to break the law of large number argument. You need some fat tails in the distribution to actually break down the law of large number argument. So what am I adding to this literature? I'm adding this simple idea of diffusion in a production network setting. So imagine there are these multiple sectors which are buying inputs from each other. What happens then? And I'm adding this additional parameter called diffusion. So what do I mean by it? So for a lot of people who have worked with physics, it's simple that it's inverse of the time it takes to react, or in the case of a gaseous medium, how quickly those different molecules, they pass around. But in case of economics, the way to think about it is the following. So most of the models which are written down are some kind of a one-period diffusion rate model. And what do I mean by that? So imagine in period T, sector 1 gets hit by this technological shock. And then it takes at least one period to impact these downstream sectors. Now, that's something which you can think of calling as a one-period diffusion model. Or you can have another kind of model where you have just one period where a shock hits a downstream sector and the downstream sector reacts immediately, and then there's a feedback loop, so the other sector reacts immediately, so on and so forth. So what you would get is some kind of a contemporaneous amplification mechanism. But once you add this diffusion, what you get is you somehow break down this amplification mechanism by a little. So it can be a little bit more tricky than that, because in the economy, it's not essential that all sectors are going to react at the same rate, which I model over here. So you can think of it to arise from various different factors. So for example, imagine there is a steel industry, and it's providing inputs to some downstream sectors, let's say automobiles and a cutlery sector. So now the cutlery sector can potentially change its decisions very quickly. So it will react very quickly to the shock in the steel sector. But how about the automobile sector? It might take a little bit longer to react because it has a longer production horizon. But you can think of multitude of other reasons as well why this can happen. Maybe the automobile sector, they write better contract or more long-term contract. So in all those cases, what you are going to see is that this diffusion rate, this same shock which hit sector 1 in period T, it's going to impact downstream sectors at different points of time. And this is something which I'm calling unequal diffusion rate. So if you have this unequal diffusion rate, what happens to the economy in case some shock hits the upstream sectors? So essentially, in the empirical side of the paper, I'm going to show that the sectoral output, it doesn't react contemporaneously to shocks in the input sectors. So this is the first thing that I need to actually establish before making this argument, that actually sectors don't react contemporaneously. And then the second piece which I'm adding here is the diffusion, that actually these sectors, they actually react at different time horizon, or they don't react to the shocks at the same point in time. On the theoretical side, I present a model to match these above empirical facts. And the most important contribution here is that how to introduce the diffusion in a production economy kind of a setting. So, as I said, it's a long literature. People have been working on this question for a very, very long time. So, in the standard case, Long and Plosser, like if you're really interested in going back and looking at how to embed network structure in a production setting, Long and Plosser is the ideal candidate to begin with. So it's one of the standard papers. And then this idea that how can sectoral shocks actually generate aggregate fluctuations, we need to go back to some of the recent papers by Eshemoglu, Carvalho, and Atale, who actually show that how these sectoral shocks can actually amplify and cause aggregate volatility. So it's the Eshemoglu paper which shows that you need some fat tail in some network statistic to actually break down the law of large number argument. Then, on the empirical side, again, it's a very difficult question to actually say whether a particular shock is sectoral or aggregate, because it's very difficult to tell from the aggregate data to distinguish these two things. So there has been a bit of work on the empirical side as well. So I'm contributing to that as well. And then in general, there is a general interest in economics now to actually model production networks and impose very different kind of restrictions on what the firms or the sectors can do. So these are some of the other papers which use these or introduce these general network topics. So I decided to skip the empirical part today, but just to give a flavor of how to actually model a production network setting. So in this case, we have a household side. So the household is a representative consumer, which economists generally mean that there is this single agent in the economy who is going to do all the consumption. And this single consumer is going to derive some utility by consuming CIT goods. So it's consumption of ith good in tth period. So it's the most simple way to actually represent it. But this consumer consumes this CIT good in every period. And then what we are doing is we are summing over all these goods, which is I equal to 1 to n. And then we are summing over the entire life cycle of this representative consumer. So it's a very standard technique, but people use it all the time. But nothing interesting is happening on the household side. The interesting part is the firm side. How are these firms actually interconnected with each other? And you can think of an n sector model where these n sectors produce these n different goods. So these are the same goods which the households are going to consume at the end, but the firms in other sectors are also going to consume these goods to produce their output. And how does that look like? It looks like following. So you can think of a given sector I producing input YIT, which depends on this labor. So each of these sectors I employ some labor, and they also buy input from other sectors. So this XIJT minus 1, it captures how much sector I is buying input from sector J. But since I said in the beginning that I'm introducing diffusion in this model, so how to actually think about diffusion? So in this case, what I'm taking as given is that these different sectors, they have different production horizons. So what are they going to do? So in this 3-sector economy case, what I'm saying is that for sector 1 and 2, they are buying inputs from period T minus 1. While this third sector, it's actually buying inputs from period T minus 2. So this is going to create some difference in how they actually react to the same kind of shocks. And then this final guy Z at the beginning, which I didn't introduce, is the technological shock. So each of these sectors is also getting this technological shock ZIT. To summarize, you can write down this complicated model, but in the end, if you solve for a planner who is actually optimizing for the whole economy, what you can get in the end is this vector of growth rate. So this delta yt is y1t, y2t, and y3t in this specific example that I have here. And you can just write it in terms of the past growth rates of these sectors and these two matrices, gamma 1 and gamma 2. And what are these gamma 1 and gamma 2? These are just the coefficients gamma ij that you saw before. So if you remember over here, there are these intensity through which sector I buys from sector J, and this captures the network structure as much as the interconnection between these various sectors. So this is what you have. So introducing diffusion, what it does is it creates some kind of a gap between how these sectors react to a single given shock in a given sector. So again, going back to introducing the diffusion, this simple model, it embeds the past models like a one-period diffusion model, which was the long and Plosser. So if you see here, it has this t-1 subscript, while a zero-period model where everything is subscripted in t. So in a simple case, you can think that this one, everything is happening contemporaneously. So you're going to generate more aggregate fluctuations. In this case, it would lead to some kind of a lag or some kind of a break in the amplification mechanism. So now, let's take a step back. So we have gotten these different growth rates in different sectors. And what we need is we need some aggregation. So we go from looking at these sectoral growth rates to the aggregate. And how do we do that? So in the simple case, we can assume that these sectors have the same weight. And then you can just write down the aggregate volatility, which is summarized by this term here. But the only important thing to look at here is this variance of the vector of growth rates of these different sectors. So in the interest of time, I'm thinking what I should exactly tell you here. But essentially, the takeaway is that if you look at the zero-period diffusion model, the one-period diffusion model, and the unequal diffusion rate model, there is some differences created because of a few terms. So if you compare the zero and one-period diffusion model, almost everything looks similar on the variance term, except that there is this lack of these few extra terms. And that creates a difference between this zero and one-period diffusion model, which essentially leads to a higher volatility in a case of zero-period diffusion model. So essentially, you can show mathematically that how would a zero-period diffusion model lead to a higher volatility. The unequal diffusion rate model, which is the more general model, will lead to even less volatility. The only other thing which I want to emphasize here is that although you are killing down the amplification in a given period because of this lag structure, but what you get through diffusion is a more persistent effect, which I'm not showing here, but essentially what this diffusion creates is that the impact of any shock is going to stay for a much longer period in the economy. So although it kills the amplification at any given period, but over a longer period, now you're going to see some impact of this shock. Which is exactly what I show here mathematically, that through diffusion, we are creating more impact over time. So if you see in a zero-period diffusion model, everything is impacted in time period t. While you can have these extra terms, t plus 2, t plus 3, and so on, in case of a diffusion model. So I didn't have enough time to present the empirical part of the paper, but essentially, we show that the sectors do not react contemporaneously to shock, and any time to build model can generate diffusion of shocks in a production network. The summation of impact over time is the same across various models. However, diffusion decreases the impact in any one period. And I'll end here with this quote by John Archibald Wheeler, that time is nature's way of keeping everything from happening at once. So that's what diffusion delivers in these kind of models.